Hello everyone, I'm Pedro Alvarez. I'm a master's student here in Brazil at Unicamp. I'm going to show you the work that I've been developing with my advisor Marx and some of the work I've been developing with the lovely Carice. And as you can see, I have the famous, oh my God, this was all. I have the famous bird right here. And I'm a physicist, so I really like this bird. This is the only bird that physicists like, apparently. And by the end of my presentation, you'll all probably be tired of the bird. But still, I'm going to try to convince you that quantum computing is a really useful tool for quantum biology and show you how I kind of managed to simulate a bird in a quantum computer. Firstly, okay, so the avian magnetoreception compass is already well established. A lot of people explained it here today, and we can see pretty compelling evidence that it is in fact light dependent. So I'm not going to spend a lot of time explaining the natural compass, but one of the proposed reactions for this process is this one of flavin and tryptophan. The reaction itself doesn't matter for what I'm doing, but as you can see, we start with a pair of molecules, then light excites one of the electrons in those molecules, cause this electron to get in an excited state, and because it was firstly in the same energy level as another electron, both of them now correlate in the singlet state. Then the electron is transferred to the other molecule, and now both of the molecules are in the radical pair state. They keep changing with an oscillatory behavior from singlet to triplet entangled states, and after some time, they recombine or in a new form, or in the original form, depending if the reaction is in triplet or singlet state. And this oscillatory behavior is sensitive to magnetic fields. So the angle between the bird and the magnetic field causes state polarization between the singlet and triplet states. That's what we can see here in those graphs. We can see that when the bird is aligned with the magnetic field lines, the singlet triplet states are more polarized, more separate, and when the bird is unaligned with the field lines, the states are less polarized. Now we have to develop, now that we understand how the reaction occurs and how the magnetic field is sensed, we need to develop our theoretical model. First, this is the simplified Hamiltonian that I'm using. It is composed of two terms: the Zeeman interaction or Zeeman interaction that gives the interaction between the field lines and the spin states of the electrons. The field lines cause the spins of the electrons to precess so that the spins align with the field. That's what this term is doing. But if this was the only thing happening, then the electrons wouldn't change from singlet to triplet. We need the other term, that's the hyperfine interaction. The hyperfine interaction happens because the magnetic field that the electrons feel in the region depend on the magnetic fields of many other nuclei around it. And this field that each electron feels is dependent on the position of the electron. So each electron, as they are in different locations, feels a different magnetic field. And so if as they feel different magnetic fields, they precess in different rates. This causes the electrons to change from singlet to triplet. So we need those two reactions to have magnetic sensitivity. Okay, and this model only takes account of two electrons and one nuclei. That's all that I'm using for now, and that's enough. So for what we want to do. To simulate the recombination, we need a more robust equation. This is the Lindblad master equation, where each part of this equation can be correlated to a part of our reaction. So the first part of the equation is the unitary evolution, or the Liouville equation. This models the oscillatory part of the reaction, the singlet-triplet exchanging. And the second part of the equation is the Lindbladian, that models the recombination, where PT and PS are the projectors in the singlet and triplet states. They basically model the recombination, and Ks and KT are the recombination rates. Here, Kc is the same as Kt, and we usually assume that Ks and Kt have the same values simply for simplicity, but this isn't always the case. To extract information from the field, we need a quantity called the singlet yield. That's this quantity. It's basically a time integral of the singlet projection of the blue line here. And after the whole reaction, we have the total amount of singlets production in the state. That's what this models. And the initial state of the reaction is the singlet state, because the electrons start in the same energy level. And by the Pauli exclusion principle, they need to have opposite spin states. That means that they are in the singlet state when one of them gets excited. That means that they are now correlated. Now that you know the whole math behind it, how do we simulate it? First, we need to take account that unitary time evolutions have the same mathematical form as rotations, as rotational operators. You can see it easily because spins processing are similar to normal precession in classical physics. We have that, but there's a problem. The terms are Hamiltonian, don't commute. So we can't just throw them in a time evolution operator or in a rotational operator. It doesn't work directly because the order matters. So we need to count that. That's what Tommaso was talking about yesterday when he said about the Trotter-Suzuki expansion. Let's think of two operators x and y that don't commute. And we want a single operator z that works as if we are applying x and y at the same time. The solution for this is a pretty complicated series called the BC8 series. That's an infinite series of commutations that goes all the way to the infinite. It's very complicated to compute that. So we can use this expansion, the Trotter-Suzuki expansion, to make it way easier. We divide x and y by n. We are changing them from really big operators to really small operators. So they are changes from big rotations in the axis to a infinite series of really small rotations. It's not really infinite because we are working with computers and computers have to approximate stuff. Sorry. I pressed the wrong button. You're right, Marcus. So that's basically it. We're changing two big rotations to an infinite number or a big enough number of very small rotations. Okay. Okay, now that we have these two, the commutation problem is fixed, and we can see the quantum circuit. This is a quantum circuit. Quantum circuits aren't like electronic circuits. They are just a visual way to understand quantum algorithms. Here, the vertical, or horizontal lines are called wires. They represent single qubits, and each of those wires is one of our spin states, because qubits are directly analogous to spin half particles. So this is pretty cool. Here, those two first qubits are our electrons because they are blue. Of course, the color of electrons is blue. And the third qubit is our proton. We read a quantum circuit from left to right, just like reading a normal text, following the arrow of time. And each of those squares are what we call gates. They are just transformations that we apply to our qubit states. This gate, for example, is the X gate. It causes the spin state it causes the state of the qubit to flip from 0 to 1 or 1 to 0. That's just this. This is the Hadamard gate. It puts our qubits in a superposition. And this little vertical line here represents an interaction between two qubits. It's called the C0 gate. And it just means that this qubit controls the other qubit in this instance. So now that we know how to read this, we can finally understand what the circuit is doing. We can connect each part of the circuit to each part of the equations. And remember, we can connect each part of the equations to each part of the reactions. So this first part of the circuit is only preparing the electron qubits in the singlet state. It's just preparing them before the evolution. The second part is the unitary evolution. This is where our Trotter-Suzuki expansion comes in. You can see we have a series of rotations that take our Hamiltonian as input. And this is directly analogous to a unitary evolution. The last part of the circuit is the non-unitary evolution. Non-unitarity means that we are losing some level of information when doing this operation. This would be the measurements in the end. That's why they look like oscilloscopes. I'm a theoretical physicist, so yeah, that's what an oscilloscope looks to me. And here, those two gates, what they do, they only change the basis of the qubits in a way that we only get results 1, 1 if the qubits are in the singlet state. But we could also change all this to a projective measurement in the singlet state. This is just more general. So now that we see that every single part of the circuit is connected to a part of the equation, we can finally get to the good part, the results. So here the blue line, okay, it's okay to read it. I was worried about that. The blue line is a numerical simulation of what I expect to see using Python, using QTIP. And the orange line is our quantum computation. Here, using a small number of repetitions in the Trotter-Suzuki, only 64, that's small for Trotter-Suzuki. And you can see that the line follows nicely our numerical simulation until some points. And what I thought at first was, oh, it's just an artifact of the approximation. If I increase the number of repetitions, it's going to get better. It didn't. So it got me to worry at first. We have a few hypotheses of why it didn't work. It might be because of the way that penny lane, that's the quantum computing platform that we're using here. It might be because penny lane uses a trotterization algorithm that's different than what we expected. It might be of different treatments of the proton spin. It has a lot of hypotheses. So the first thing that I tried was to run it in another device. I use IBM's Qiskit to get better results, and I got better results. Here we have our numerical simulation in the left, and on the right I have my quantum computation. And the upper graphs are non-normalized, and the lower graphs are normalized. So the results, the lines are better. We have a better shape here than we had in penny lane. We only have a problem that in the non-normalized version, the curve is squished, if you look at the vertical scale here. And in the normalized, the normalized version, the upper one, the curve is translated upwards by about 4.5. We are still trying to understand why it's happening, but I think although we have these unexpected effects that might be because of the way that we are calculating the yields in the end of the circuit, we can see that the vertical scale here has about 0.1 scale from the lowest point of the curve to the highest point. And this is the same scale as the numerical simulation. So although it's translated, the curve has the same shape and about the same scale. So it's a good result. It's a good way to start working with quantum computations, especially for a digital device that usually isn't what we use for this kind of simulations. But I hope that this is just the start of a great digital laboratory that we can use to test and comprehend our models of the radical pair reactions and of other spin-dependent chemical reactions. Thank you.
Questions to Pedro?
And I hope that you saw that I had one bird in every slide.
Hi, Pedro. Thanks for the talk. I have one technical question, which probably will not translate into 3/4 or 4/5 of the audience. And another one is more regarding your simulation. The technical is that the Lindblad equation that you showed seems to be missing something. As it is, I don't think it preserves probability. So, but regarding your simulation itself, so the way that I am understanding, you're doing like this. You're doing the unitary evolution first.
Yes.
And then you are doing the non-unitary part.
Yes.
So in principle, I wouldn't expect this to really match your numerical calculations, because it would be better if you could intercalate, do a tiny bit of unitary evolution, a tiny bit of non-unitary part, a tiny bit of unitary, a tiny bit of, that would probably approach much better your.
Yes, that would probably, but when we measure a qubit, we destroy it, so you can't reuse it. I'm working on some algorithms that might do what you are saying, but what I do here to get the results, I don't run it once. I run it a few times for a certain amount of time, then a few more times for a bigger amount of time, and do that until a point that I'm satisfied with. So I'm not running the circuit once. The circuit simulates only one reaction. If we want to simulate the bird sensing the magnetic field, we need to run it at least thousands of times to simulate all the reactions that the bird would feel. So we are running the circuit thousands of times for a lot of different periods.
Hello, Pedro. Thanks for a nice talk. And I have actually two questions as well, similar to Marcelo. But one is very general. You might comment first. The other is more technical. But more general is, I mean, what are you planning? I mean, in the long run, I would say, with running in a quantum computer. Because nowadays, I mean, I understood that your numerical simulation is better than the quantum computer. When you are envisioning that it is going to be better to use the quantum computer.
Well, the quantum computation is faster than the numerical simulation. The numerical simulation takes a few hours to a few days to run, and this is because I have a very simple simulation. If I had a more complex simulation, it could take weeks. And the quantum computation only takes a few minutes to run on the actual device. It takes longer for me to wait on the line to access the device than for the circuit to actually run in it. So we gain some time, and the objective that I have with all this work would be to create a simulator of chemical reactions that everybody can use, that is open access, so that you wouldn't need a cluster, a really big cluster, or a laboratory to actually understand those models, because the quantum computation is closer to reality than the numerical simulations. Quantum computation actually uses quantum mechanics to run it.
Well, it's good that you brought this point, because I mean, I agree in principle, but once you are trying to simulate a Lindblad equation, then probably you are losing actually your quantum advantage. Yes. Because you are actually trying to simulate a semi-classical system in some ways, because you are adding the lack of knowledge. Mm-hmm. And so then you enter in a more fuzzy situation. And that's what I think Marcelo called the attention. It looks strange when you order things the way you did, because in the master equations, everything occurs simultaneously. Yeah. So I would expect, if you want to have a coherent evolution with some sort of jump of measurement, usually I would expect something more looking like a quantum Monte Carlo simulation, that you have really something that's coherent, and then you run through a point that you randomly choose, and then this random choice that you include your lack of knowledge. No? But I wouldn't expect something like what you did, with something that is deterministic, and then with just a decoherence in the end. That's what I'm saying. Okay. Thanks.
Okay. Sorry, I haven't seen.
Yeah, so those are good points. Yeah, but I sorry to answer that, but this is actually a good point to answer. What he's doing really is simulating a specific model. So it doesn't need to be, as Marcelo has noted, it doesn't preserve probability, because it's not really a Lindbladian master equation. So it's a way that you actually simulate the yield that you have at the production of this specific end product that you have for different reactions. So this is more similar to a rate equations than really a Lindbladian equation, but you can actually do this. But if you want to do something which is closer to the reality in the way that you have to simulate, every single interaction, and also adjusting the system as you to consider, for example, the action of the external noise, as I considered in my presentation, then you would have to add lots of qubits, to simulate a non-unitary channel. So this is actually quite complicated. So in the end of the day, I suppose the best way to do this is to simulate a master, like a stochastic state evolution. So that's the way. But then what he's doing is like a more phenomenological way, by substituting a single time step and simulating many time steps. So he simulates in the way that he has described it. So he has unitary evolution and measurement, unitary evolution and measurement, and so on. So that substitute as well. The result is similar. well, it's to be compared whether this is better or not, okay? And the end result is actually to extend this to many more states, so in a way that we can have actually a simulation of a larger molecule.